Everybody expects that in hot places, you're going to have air conditioned buildings. But in many places of the world, it's definitely not. And we've got to find solutions, which I think by making air conditioning more efficient, we make it more accessible and more affordable for people that need it the most.
Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hello and welcome to Hardware to Save a Planet. I'm here with Ross Bonner, the CTO and co-founder of Transaera. Ross and his team have an approach to air conditioning that uses 40% less energy than conventional systems, and it works to cool buildings in hot and humid climates, which is important. I'm keenly interested in this space. Cooling our buildings accounts for about 10% of global electricity demand today, and that's despite the fact that most people in hot countries still don't have AC. Of the 2.8 billion people in the hottest and poorest parts of the world, only 8% have AC in their homes. In contrast, in the US, around 90% of homes have AC. So this is a problem that really highlights the inequality in the way climate change is impacting the world. Finding a way to cool our buildings efficiently is especially important because as incomes rise, populations grow, and temperatures increase due to global warming, the demand for AC is expected to triple by 2050. The International Energy Agency projects we'll need 3.3 billion more AC systems in the next 25 years. This growth in cooling is definitely a good and necessary thing in that cooling benefits human life and productivity, but we must do it as efficiently as possible to minimize exacerbating global warming even further. I'm excited to hear more about all this from Ross. He co-founded Transaera with a background in systems architecture, fluids, and heat transfer. He's a graduate of GE Aerospace's Edison engineering development program. He earned his bachelor's in mechanical engineering from Auburn University and his master's in mechanical engineering from MIT. I've had the pleasure of bumping into Ross at a few conferences over the years, and I always appreciate how friendly and humble he is, mixed with this intense drive to make a positive impact through his work. So, Ross, it's really an honor to have you on the show. Thanks for joining.
Dylan, thanks to you for the great intro, and it's great to be here with you today.
So, you spent the first part of your career in aerospace at GE. I'm curious, how did you end up landing on cooling as the problem you wanted to solve?
My career definitely took some twists and turns along the way. Like you said, I started off, my background is in mechanical engineering. So did my bachelor's degree at Auburn University, and then straight out of school, started at GE Aviation. And for someone like me, who's very passionate about mechanical engineering, I think I kind of found my fit with engineering in general. I'm a natural problem solver, love tackling kind of complex problems like that. Aerospace is a really great industry to be in, especially at GE Aviation. We do turboshaft and turbofan engines. So these are jet engines, essentially. And under the hood, these are incredibly complex machines, right? It's blades turning at crazy high speeds, and it's got like high stresses and high heat, and it all has to fly, so it has to be lightweight. And so it's kind of it's an engineer's playground there to be able to like work on those designs. And I got to work with some really brilliant people and learn from some great engineers while I was there. And I reached a point in my career where I kind of realized two things. One was that I wanted to point my career in a direction to have a greater impact on the direction of the company, which meant going somewhere smaller. And I wanted to do something about climate change. And so I went back to school, did my master's in mechanical engineering at MIT, and I actually had this kind of life-changing, like it's total coincidence, and I didn't know it at the time that it would be, but life-changing moment where one of my classes there early on was like a design and build class. And every year they do some targeted topics. And the year that I I was there, there was one which was like an autonomous boat with some sensors to help improve GPS navigation. And the other was called carbon neutral cooling and kind of ambiguous. And so my friend that was taking the class with me at the time, we were texting and registering and getting signed up for the class. And he texted me, okay, so we're going to do robot boat or super fridge. Super fridge sounds cool. Let's do that.
Yeah.
And now here we are, like 6 years later, that's kind of become my career focus because I just fell in love with the problem. Like you mentioned, it's a really huge problem. And at least at that time, there weren't all that many people paying close attention to it. So it seemed like a natural fit where I could pour my energy into and potentially have a really big impact on climate.
Yeah, man, what a great argument for kind of intentional curriculum design too, and the power that can have.
Yeah, absolutely. I mean, through that class, I basically learned the scope of the problem. There were a couple of key publications at the time that were looking at kind of like McKinsey curve type rankings of what are all the type potential impacts and areas of impact that we can have for climate change. And HVAC and refrigeration was like right there at the top. And I thought, that's interesting. I've never really thought about air conditioning as a climate technology or a potential for climate impact. But the more that I learned, the more that it seemed like this really could be a good fit for me. And even though it's pretty far from designing jet engines, it still does carry a lot of those same like thermodynamics and fundamentals that I get excited about. So yeah, it fit really well with where I wanted to take my career. And I met up with my co-founders at Transaera through MIT. They were actually around the same time coming at the problem from a different direction. So we'll talk more about Transaera's technology in a minute, but we use these materials called metal organic frameworks, which one of our co-founders, Mircea, his lab at MIT has been working on these materials for 15 years. And Serene Grama, our CEO, had linked up with him. Both of them are Romanians, and they bonded over that and decided to start a company aiming to find a good commercial use for these MOFs, metal organic frameworks. And at the same time, I was looking at how do we make air conditioning more efficient. One of the ways that we can do that is with new materials. So kind of Reese's peanut butter and chocolate.
That's good. I've definitely in some ways in my head, I categorize different climate tech startups as either sort of having a solution, looking for a problem, like they have the material, they're looking for the place to apply it, or sort of having the problem, looking for the solution, like you want to go solve cooling. But it sounds like this was sort of a perfect meeting of the two.
Yeah, exactly. It was kind of those two things come together and meshed really well.
So I have this tendency to think about, climate tech, I get sort of tunnel vision on like atmospheric CO2 concentration and, temperature increase and this sort of the technical aspects of climate change and fighting climate change. But I know that there's this side of the story that's about human health and survival, and productivity, quality of life, and equality. Could you help me flesh that out a little bit more? Like putting climate change aside, why is cooling so important to humanity? And to what extent does that drive you?
A great one. You mentioned it at the outset, but at its core, really, air conditioning is an equity issue. About 1 in 10 households in the US don't have access to air conditioning. The US, where many of the places where people live have very mild climates, and 90% of those people have access to air conditioning. Meanwhile, in India, about 1 in 10 households do have access to air conditioning, and the climate there is punishing. It's hot and humid most of the year. And so when we think about that with the backdrop of climate change, those conditions are only going to worsen, and that disequity is only going to worsen. And it really does become a survivability crisis in some parts of the world. There are limits to the kind of maximum wet bulb temperatures that human life can sustain. We cool ourselves by sweating, right? And beyond sweating and evaporating that sweat, we don't have a mechanism to stay cool. And there are places in the world that are approaching those kind of limits. And as the world continues to get hotter, those places will potentially have some big human consequences. So I think that air conditioning in the US, it is kind of taken for granted, right? It's everybody expects that in hot places you're going to have air conditioned buildings, but in many places of the world it's definitely not, and we've got to find solutions, which I think by making air conditioning more efficient, we make it more accessible and more affordable for people that need it the most.
Yeah. And one thing that's always kind of stood out to me is like, or as I've learned more about this, is survivability is definitely a big thing. But even before we get to that point, just like I've seen studies about productivity decreases as temperature gets above, even like, I forget what it was, like 75 degrees Fahrenheit or something, like productivity or cognitive function start to drop off. And if you just think about like, these parts of the world, like rising out of poverty and just sort of equity in general, like that feels like a really sort of crucial, like table stakes need that needs to be met in order to get there.
Yeah, 100% agree. I mean, I think it is a little bit of an invisible problem or something that those of us in the US don't think about all that much, but certainly in those areas where there's not universal access to air conditioning, there are real impacts to that on productivity and cognitive function, like you said. So I think bringing technology that can help make that available to a wider population is a worthwhile mission.
Yeah. And then just to look at it from a pure climate change perspective, I'm curious kind of how should we think about air conditioning? What are the biggest impacts? I know refrigerants are bad. I know the energy consumption is a problem. Purely for climate change purposes, like what is the biggest impact and what are you doing to mitigate that?
Yeah. So you can kind of separate out into different buckets the climate impact from air conditioning. And there are really three that are the core impacts. About equal thirds are the refrigerant itself, the latent cooling, which is dehumidification, and the sensible cooling, which is reduction in temperature. So those three buckets each are about equal in how much they contribute. And then a small fraction is sort of the embodied cost, the energy to build the AC and all that embodies there. So looking back at those three, the refrigerant is a problem that is being addressed. We have that 1/3 represents sort of where we are today with today's refrigerants, which have a high global warming potential. So today in the US, the most common refrigerant for comfort cooling is R410A. And that has a global warming potential of about 2,000. So for every pound of refrigerant that is released into the atmosphere, it's equivalent to 2,000 pounds of CO2, which is why refrigerants are so tightly regulated and controlled, because a little bit goes a long way towards warming. Luckily, there are kind of regulatory mechanisms to phase out those older generation of refrigerants, and that's happening. So that roughly 1/3 of the problem is on its way to being solved. There's a new generation of what they call low GWP refrigerants that's being rolled out now. And down the road, we actually have line of sight to even more environmentally friendly refrigerants, a class of refrigerants called natural refrigerants, which have some other issues around flammability, do offer kind of a full solution to the carbon impact. That's refrigerants. And then the other 2/3, now if you imagine fast forward 5-10 years and call that part of the equation solved, then it comes down to about a 50-50 split between the sensible cooling, reduction in temperature, and the latent cooling, reduction in humidity. Transaera is focused on is that latent cooling. The dehumidification loads really shouldn't represent that much of the total energy of the device. And maybe to set context here, the remaining carbon footprint of the device is from use. So it's the energy used to power the device.
Used to either dehumidify the air or reduce the temperature of the air.
That's right. Yeah. And so the fact that dehumidification is actually more than half of the total power consumption of an air conditioner, it's really because the way that the device works today, it's kind of an inefficient solution. AC today works by something called dew point dehumidification. And this is a process that's really been around since the days of Willis Carrier, the father of air conditioning 100 years ago. Carrier was solving for a dehumidification problem, actually, in a paper plant or a printing facility. And what they found is that over the season, varying humidity levels caused problems for printing. And so he came up with a way to dehumidify and keep those humidity levels consistent. But what he did as a consequence was also kind of invented air conditioning to handle the thermal loads. And it turns out, ironically, the solution he came up with is quite efficient for handling sensible loads, the temperature loads, but it's quite inefficient at dehumidification. And there's better ways to do that. And that's what we're exploring here.
Yeah, say more about that. How does your system do that in a better way?
Yeah, so Transaera uses this new class of material called metal organic frameworks, or MOFs. That's MOF. And these are a pretty incredible and broad class of materials, but they're able to pull moisture from the air like a sponge. These are crystalline solids, and they're made up of metal clusters and organic linkers that sort of join together in this like repeatable cage-like structure. It almost looks like some kind of like Tinker toy, like toddler toy, but it forms cages, and these cages are repeatable units. And by controlling which metals and which linkers are used, you can actually tune metal organic frameworks to target a specific species. In our case, we're targeting pulling water out of air. And you do that by changing the size of those pores so that it's tuned to the size of a water molecule. And what it results in is that we're able to have a material that can pull water from the air above the dew point. So it doesn't require that dew point dehumidification, this inefficient process that today's systems use. And then maybe even the more important trick is it holds it on the surface or kind of in the MOF itself, in the solid, but then it's able to release it again with just a small amount of heat. So what we're able to do is use the waste heat, which is already present in any air conditioner, to regenerate the MOF. And so we can pull water from the air and then hold it there for a while and then use waste heat to drive it back off into the air. I think the biggest differentiator for our technology is really its simplicity. We've talked about how we're using this desiccant wheel architecture that is already something that has been out there. And we use already commoditized equipment, compressors and evaporators and heat exchangers. I see a real potential to achieve scale rapidly because of the simplicity. And then furthermore, what we've heard from customers over and over again is they want simple is key, right? They want a simple drop-in replacement. And that's what we've built. Our device, it sits on a standard curb. It can be installed by HVAC technicians the same way that they would install a conventional system. The same electrical hookups and all of the ancillary equipment kind of surrounding it is identical to what's out there today. And I think that's a real benefit that we have that can allow us or enable us to work with manufacturers to achieve scale quickly.
Yeah, it sounds like you sort of architected it, to optimize for easy adoption, reliability, low cost, like simplicity really drives a lot of those things. Was that, I know sometimes getting to the simple solution is actually a really challenging, complex road. Was that the case here? Was the idea from the beginning fundamentally simple?
No, that was 100% the case for us. And my winding road didn't end when I started at Transaera. We went through many iterations of trying to use the MOS in the system, and some of them were really complicated, and maybe they had really high potential energy savings. I think the lesson for us and for me over time is that 80% their solution that is very simple will always beat the 100% solution that is very complex. And so achieving the simplicity and the readiness for industry adoption is really key for us.
Has that come through a lot of kind of customer research and interactions? Is that where a lot of that comes from, is really understanding what's going to make this more adoptable?
Yeah, I mean, it's been a lot of working with customers, working with partners, understanding the industry, and hearing that over and over that, man, it's got to be simple. I don't want to have to think about this too hard. I just want to see the energy savings. And if it's doing that and I don't have to change my installation story, then that's a winner. You don't need to convince me further than that. I think that's what we've heard over and over again. And because we're using a form factor that is already out there in industry and technicians are already trained on how to service desiccant wheels, it's a really simple procedure. You can actually think about it on the same level as like filter changes, basically. So that simplicity in installation and in service and maintenance is a real differentiator for us.
Okay, so now you have me curious. Are you selling to or working with the sort of carriers and the trains of the world, like the big incumbents? These are your customers or partners?
Yeah, so right now our goal is to prove out the technology, and we're going to do that in the form of full prototypes with customers.
Right, these rooftop units you're talking about.
As we scale, the longer term goal is to integrate with the manufacturers, the carriers of the world. And that's how we think we can get to scale fastest. And it also allows us to have the focus that I think we need to scale the core part of the technology and continue to develop that while allowing our customers and partners to continue manufacturing the HVAC equipment that they already have optimized.
You don't need to reinvent the whole system.
That's right.
Yeah, your stuff on top of their stuff is the magic. Yeah, I was just asking because I was kind of curious if you know or how you believe those incumbents will view you, like as a threat or as a benefit, somebody to acquire, or what that looks like.
Yeah, I mean, I think that's another differentiator for us, is that we can work with the OEMs and innovate from within rather than try to go head to head with them.
And just to kind of make sure I understand, a purely kind of evaporative cooler doesn't have this stage of drying the air out, right? You're just sort of taking the advantage of this effect of when water goes from liquid to gas state, it absorbs energy, it absorbs heat to make that transition and kind of pulls heat out of the air. But what you're doing by adding this ability to dry the air first is enabling your system to work in places where the humidity levels are higher. Is that the way to think about it? You're drying the air out so you can take more advantage of this effect of sort of evaporative cooling in the second stage.
Yeah, so our system actually uses a conventional vapor compression to do the cooling. It doesn't really use the evaporative cooling directly, but what it does is dehumidifies the air without the need to overcool. So to go back to this dew point dehumidification, which is what's used in most every air conditioner today, that requires bringing the air down well below the dew point so that the water collects, it beads up on the surface of the coil like water on the side of a cold glass, and then runs off. And to get To actually achieve that function, you have to cool air well below thermal comfort and what it really needs to be cooled to. So, because we don't have to do that, we can actually run at warmer evaporator temperatures, which kind of getting to the fundamentals of like how an air conditioner or heat pump works. You have a cold coil, the evaporator, you have a hot coil, the condenser, and you have a compressor that's cycling refrigerant through. And the difference between that high pressure, the condenser, and the low pressure in the evaporator scales with the amount of work that the compressor has to do. So if you raise the evaporator temp, you reduce the work and make the entire cycle more efficient.
So actually, it's like you're adding this kind of drying stage to the front end of a conventional air conditioner.
That's right. And what it enables is operating at a more efficient design point. And that's where a lot of that 40% energy savings comes from.
That's super helpful. So these MOFs, and just to kind of, I think MOFs are really interesting because they actually come up in the carbon removal space as well as a way to sort of absorb CO2 from the atmosphere. I've seen MOFs in a lab, and at least what I remember seeing just looked like sort of a white sheet or like this white coating on a sheet, right? The structure you're talking about is very microscopic.
Yeah, so MOFs are nanoscale. So this framework, all, molecular level structures. And it's funny, like anytime I run into anyone with a chemistry background, a lot of times I mention I'm working on MOFs, they're like, oh, I've made a MOF, because that's like kind of a common, like later level chemistry class trick is like, oh, today we're going to make a MOF. And they actually are relatively simple to make, really difficult to get very good quality. And so that's kind of where we're focused. And then I think the key detail to keep in mind is MOFs, as they're created, are basically a powder, right? And they've been around for 15, 20 years in research, and they have a lot of applications. Like you mentioned, carbon capture is one. But in order for them to be scaled and really used at scale, they need to be applied to a surface and integrated into a system. And that's what Transaera is doing. So we're actually taking MOF and we've created a coating using that MOF and incorporated into a device that has that coating.
The challenge I've always heard about MOFs is that they're great in the lab, but they're sort of not available at scale and very expensive and all of that. I don't know, what do you think about that? Or how true is that in Transaera's world?
It's funny, it was absolutely true 2 or 3 years ago. And we've seen as the company has grown, luckily we just kind of lucked out on timing here, but through some other industries like carbon capture, you're starting to see MOFs be produced at scale. And this is being taken care of by other companies. So there are MOF manufacturing companies that are starting to pop up and produce at the kilogram and ton and megaton level to make that available. And now that part of the equation is not now a problem that we have to solve. It's a problem that we fortunately is being solved through other means. And so because that cost curve, as we're seeing that cost curve come down, allows us to scale up, and it also increases the pool of different MOFs that are available and just the general knowledge base around MOFs. I mean, these are new materials, so there's a lot of characterization that has to happen as they begin to scale up. So we're seeing that learning happening, and we're able to sort of piggyback off of an industry that is growing on its own.
And then in terms of where you're innovating and putting your kind of development efforts and engineering efforts, it sounds like the drying stage and the application of these materials is really where Transaera's IP is. Is that right? Are you kind of focusing on that stage and then you'll integrate with existing technologies and HVAC manufacturers and everything for the rest of the system?
Yeah, that's right. So we use a type of device called a desiccant wheel, which is really a very high surface area wheel. If you look down like on the edge of a piece of cardboard, like packaging, and you see the little flutes.
The corrugation?
Yeah, those corrugations. So you can imagine taking like a sheet of cardboard and slicing it and then stacking up a bunch of those. That's close to the geometry that these devices are. And it's aimed at just generating a lot of surface area, right? And so you put that into the form of a wheel and then rotate it through these two different air streams. And so it goes through on the process side. This is the air that's coming in from outdoors or that's being conditioned. And that air, maybe it's hot and humid. It goes through, it interacts with the MOF and adsorbs the water out of the air into MOF. And then that rotates through. And then on the other side, we use the waste heat of the cycle to drive it back off. The water actually never becomes liquid. It's just, it goes into the MOF, hangs out for a while in the wheel, and then comes back around and then gets desorbed or kicked back off on the other side.
As a vapor.
As a vapor, yeah.
And where does that go?
So that gets exhausted back to the ambient air.
Okay, back outside.
Yeah.
What's the sort of time duration of that cycle?
It can vary depending on the climate conditions and depending on kind of the other operational parameters of the device, but it's on the order of minutes. So these are not super fast rotating wheels. They're kind of slow moving. And I'll also say that desiccant wheels are also a technology that does exist and has been around for a while using other desiccants like silica gels or zeolites. And the problem that hasn't really had a good solution until now is with those other desiccants, in order to regenerate them, you need really high grade heat, high temperature heat. And so the types of systems that use desiccant wheels today, these are like very, very niche applications for things like ice skating rinks where they need very low dew point supply air. But they're extremely energy intensive because you're basically burning natural gas or running a resistance coil to get to that very high grade heat. And with the MOF, we're able to achieve that same level of dehumidification, but regenerate it using heat that's already readily available and actually benefits the cycle instead of burdening it.
Right. From an energy standpoint, you get that dehumidification for free.
Essentially, yeah.
Or very, very close to it. Yeah, because that's otherwise just wasted heat. Are you designing and building kind of these dehumidification wheel-based stages that you would then supply to HVAC manufacturers?
Yeah, so what we're working on right now is we have just this year, we built our first scale pilot. So this is a commercial system. It's actually a class of rooftop unit, like the units that you see on commercial buildings, called a dedicated outdoor air system, or DOAS. And these are the units that are responsible for ventilating commercial buildings. They bring in 100% outdoor air, and then they condition it to room conditions, like to neutral conditions, and then supply it to the air or supply it to the space. And these units, you might imagine, they really have two problems. One is because they're taking in outdoor air in hot and humid climates, they are real energy hogs, right? They're taking extremely humid air, and a lot of that load comes from the dehumidification. So this is a kind of a beachhead market for us because it's a pain point in the industry where these units don't have a great solution today. They're very energy intensive, and any solution that can reduce the energy burden is welcomed by customers.
What have been the biggest technical hurdles you've had to overcome so far, or what is on the kind of on the roadmap for you? What other technical risks are sort of keeping you up at night?
I think we've got a really good fit here with the commercial units. And I guess I'll say some of the technical hurdles that we've overcome are really just finding that product market fit, finding where to apply the technology and where the need is the greatest. And I think we've got a good fit there. Yeah, I think the next phase for us is around taking that prototype and commercializing it. So there's a lot of execution, there's a lot of working with partners and manufacturers to scale up that solution, but I think we have the basic blueprint. And then on the development side, it's continuing to optimize and find just the right combinations of the moss and all the other things that go into the coating and combining those with the geometries that optimize the performance of the wheel. But I think that's a playbook that is pretty well defined, and we already have sort of met that minimum bar that proves viability. We believe that there's actually a long way to go still and further improvements that we can make. And that's our internal development focus, and then commercialization along the same timeline.
You talk about serving the hottest and poorest parts of the world, like in your recent press releases around your recent funding round. What does it mean to build a product and business for that market? Is that just kind of driving costs out of the system as much as possible? What does that look like?
Yeah, I mean, I think it really is a dedicated focus on cost, and that's going to come through scale. So our focus now is in the commercial space. We are starting off in the US because that's where we have a foothold. As we grow, our ambition is to get this technology into the hands of the people who need it most, and those are other countries and places in the world with climates that demand it more than the US does, honestly. But I think to get there, we first have to scale up to even have a shot with the cost reduction that we need.
So your first markets will be US, sort of Europe, kind of places where you'll have higher margins and lower volumes as you scale and come down the cost curve.
Yeah, that's the general playbook.
Maybe it's a little tangent, but I'm curious, like how investors look at that as the long-term goal. It is a volume play, but I imagine margins are much lower. Like, is that purely like sort of an impact investing angle, or do investors see that as a big opportunity to go impact that part of the world?
I think that there is the potential, if I kind of imagine several years down the line for us, if we achieve that level of commercialization, then there are opportunities to maybe we have a spinoff that is dedicated to serving those underserved markets. And that would be targeting an investor, maybe an impact investor, to bring that solution to where it's needed. I think that in general, the technology is a platform technology. There are applications quite broad for this. This dehumidification being sort of the Achilles heel of air conditioning is across all verticals. And commercial makes sense for us to use as a beachhead, but we would love to, through partners and through other mechanisms, get this technology out there into as many different markets as we can.
I mentioned at the beginning 3.3 billion more AC units in the next 25 years, which is just kind of this like crazy number, right?
Yeah, it's a staggering number. Some of my earlier pitches were trying to put some sense to that number. The statistic that always stuck with me was, this is a couple of years ago, but there are about 2 billion air conditioners out there in the world functioning today. And that's about the same as the total number of iPhones that have ever been sold. So
right.
It's like a mind-boggling number. And yeah, I think on that opportunity, kind of coming back to what pulled me into this, trying to solve this problem, it's a really motivating thing that we could actually serve a market that size, right? Like our solution could find its way into the hands of potentially billions of people.
What do you as a business need to accomplish or what needs to change externally to enable that kind of success?
I think right now we are on the cusp of building out this first generation, this first platform for the commercial market. But I think that as we see that succeed and prove it out, that the energy savings are there and that the longevity is there and the reliability and all the other things that customers care about, I think that's where we make space for further expansion into new markets. But I think that's a problem that's going to take years and maybe decades to really get to that level of scale. It's for us, what I'm excited about is seeing that kind of newborn phase of first of a kind, first time putting this coating into this device and seeing it perform and actually seeing what we had modeled and worked out on paper manifest in a full-size system was extremely exciting. And so I think looking ahead now to the next year, we want to replicate that and make it scalable and begin that commercialization process.
Yeah, there are many, many steps on that journey.
Yeah, absolutely.
Okay, I have 3 last questions for you. The first is, how optimistic or pessimistic are you about the future of the planet and why?
This is a tough one for me. I think that I'm somewhere in between. On the pessimistic side, if I just sort of put on like my project manager hat and look at where carbon emissions are today and how they've tracked against where we all know they need to go, we're not there and we're not really approaching where we need to go fast enough. Even today, we're at the point where we're staring down the barrel of some pretty severe consequences, pretty much baked in. However, humans are incredibly resilient and resourceful, and I think we will continue to find ways to innovate and to adapt. And what I see in the startup community and the climate tech community is a lot of really motivated and really innovative people solving problems that can have an impact at scale. But I think that long term, we are looking at kind of a blended model of adaptation, and we should prepare for what that looks like. I think it speaks to how much of a challenge it is, and if we're just realistic with it, there will be effects that we should all prepare for in our lifetimes and beyond, looking at the next generations.
Who's another company or individual doing something to address climate change that's inspiring you?
I have 2. The first is Elemental Impact. So Transaera is a portfolio company of their accelerator program. I think that they've been on the show.
Yep.
So they have a focus on equity. And like I mentioned earlier, climate is at its core an equity issue. Those with the least resources are often the most affected by climate change, and they're trying to address that. And then the second is a company called Fleet Robotics. We're actually sharing some lab space with Fleet right now, but they are building these small autonomous robots to clean the hulls of ships. They look like the hoverboard from Back to the Future, and they kind of like crawl along the side of the ship to clean off the barnacles and the slime and sludge and stuff to make ships more efficient. So it's a really cool application. I think it shows kind of a leverage effect that I just love to see. There are some startups that really nail that, where they can take a really small thing and have an outsized impact. And I think Fleet does that.
Yes. Somebody else has mentioned them. I would love to talk to them. What advice do you have for someone not working in climate today who wants to do something to help?
I would say, obviously, jump right in. Come join us. We need all the help we can get, all the warm bodies that we can get. I think it's extremely rewarding work. And as someone who has started out their career not in a traditional climate tech role and joined the fight, it's just been an incredible experience. I think that it's an inclusive community. I think that maybe from the outside, it can appear like kind of well, hang on, in my own life, if I'm not fully carbon neutral and drive an EV and skateboard to work or whatever, are they going to be accepting? And I think you can kind of dispel that notion entirely. It's a very accepting and inclusive community with a big tent.
I've found that too. Awesome, Ross. That was really fun. Thanks a lot for your time. I've learned a lot. Appreciate what you're doing.
Dylan, thanks so much for having me. It's been great talking with you today.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.